Okay, so in this presentation, I'm going to talk about data flow and behavioral modeling, the difference between these two. I'll talk about Verilog operators. Well, we have already seen some operators, but I'm going to talk about additional operators. So Verilog provides a very rich set of operators that you can use. The meaning of module parameters, okay, how to model adders, comparators, multiplexers, the always block, the meaning of the sensitivity list. So we use it for behavioral modeling in Verilog. I'll talk about procedural statements, the if statement, the case statement. We can use them, okay, to model circuits in Verilog. How we can model a decoder, priority encoder, ALU. So all of this will be shown in this presentation. So this will be the topic today and next week. Now, Verilog defines a four-valued logic, which means that we have four basic values in Verilog. We have 0, that indicates logic 0 or a false condition. We have 1, this indicates logic 1 or a true condition. We have X. Now, X here does not really mean it don't care. It means an unknown logic value. So this is shown, for example, when you are using a simulator and it shows to you that the signal is shown in red. So red here, it means that the value is unknown. So it means unknown or uninitialized value. We did not assign a value, okay, for the signal, and therefore the value is unknown. So it's not 0, it's not 1. We don't know what's the value of this signal, and this is shown as X. So that's the meaning of X. It could be lowercase x or uppercase x. It does not really matter. They both mean unknown. We also have Z. Z is a fourth possible value in Verilog, and it indicates high impedance value. We have seen in my last lecture when I talked about multiplexers and the three-state gates or tri-state gates. So the tri-state gate or the tri-state buffer, it's a gate that can have its output in the high impedance. So you have this fourth possible value in Verilog, and when you see the output is Z, it means that the output is a floating wire. The output is disconnected from the input. Okay, so this can happen if you are using a three-state gate in Verilog, and you can see that the output is Z. It could be lowercase z or uppercase Z. It's not really case sensitive. They both mean the same thing. So that's the meaning here of high impedance. It is used in some gates in which the output can be disconnected from the input. Right. Verilog also has two major data types. So it has the net data types, and we have the variable data types. So these are two major data types that we have already seen in before, okay, in Verilog. So in the case of net data types, these are connections between different parts of a design. For example, the wire. We use wire. Wire is a net data type. It indicates a physical connection. It cannot really store a value. We cannot actually use the wire to store the value of let us say, in a procedural assignment. So we cannot actually use a wire to store a value, to store a 0 or a 1. Okay, so it can be driven by continuous assignment. That's the wire. So we can use a continuous assignment to drive a wire. So it could be the output of a gate, or it could be the output of a continuous assigned statement that can describe some logic, okay, in your circuit. So that's the wire. So it's called a net data type because it indicates connections, okay, between different parts of a design. On the other hand, we have the register. The register is a variable data type. So here you can store the value inside a register because it's like a variable in a high-level programming language. And you can use it in a procedural assignment. So in the case of a procedural assignment, you can assign a value to a variable. So that's the register data type. However, you cannot drive it with continuous assignment. You cannot use the assign statement to assign to a variable. You can use it to assign to a while. You can use continuous assignment to drive a while. But you can use the procedural assignment to assign the value of a variable. Okay. There are also other variable data types like integer, time. These are also variable data types. You have time, you have real time. All of these you can use them in Verilog. So these are also examples of variable data types. Now, when we model circuits in Verilog, okay, there are different ways of modeling. You can actually model it at different levels. The lowest level is what we call the gate level modeling. We have already done this before at the beginning of the semester when I introduced Verilog. So we can use primitive. So Verilog defines primitive gates, like the AND gate, the OR gate, the NOT gate. We also have NAND, NOR, XOR. All of these are primitive gates. And you can use keywords in Verilog to describe these gates. So this is the lowest level modeling in Verilog. Okay, so this is called gate level modeling. We have structural modeling. Here you are going to use module instantiation. We also have done this before. They call the module instantiation statement. I talked about it in a previous lecture. So here we can use the module instantiation to create instances of modules inside other modules. So we are describing the structure of a circuit. So we use module instantiation for describing the structure of a circuit. So you can describe it using modules at different levels. Okay, so you can instantiate modules inside other modules. Okay, as if you have a sub-circuit inside a circuit. So you can do this at different levels. Okay, so you can actually have multiple levels of module instantiation. So this is the second level, okay, of modeling a circuit in Verilog. The third level is what we call here data flow modeling. So data flow here, we are using concurrent assigned statements. So we are using the continuous assigned statement. And you can have many of these. And if you use multiple continuous assigned statements, then they become concurrent inside your description, inside your module. So here you are describing the flow of data from the inputs to the outputs. Okay, for example, we have already seen that, and we can use it, for example, to describe, let us say, a binary adder or a BCD adder. So this can be easily described with continuous assignment. So this is the meaning of data flow modeling. And the fourth level that we did not really do it so far, already we have seen continuous assignment and data flow modeling, but there is a fourth level which is called behavioral modeling. This is something new. So here we can use procedural blocks and procedural statements. And what we are describing is that we are describing the circuit at a higher level of abstraction, the same way that we describe software. So we can describe it algorithmically. We can use statements, case statements. We are going to see all of these as examples about behavioral description. So we need a procedural block, like the always block. And we can write inside this block, we can write procedural statements. Not only that, but we can also mix. You can, for example, have in the same module, you can mix between behavioral modeling and data flow modeling. You can also mix between data flow and structure. In fact, you can mix all of them. In the same module, you can actually have all of these. You can actually use gates. You can have structural modeling using module instantiation. You can use the continuous assigned statement for data flow modeling. And you can use, for example, the always statement for behavioral modeling, and use the procedural statement inside the always block. Okay. So we can mix. So this is actually very useful, okay, in Verilog and very flexible. So Verilog is really a very flexible hardware description language. Fine. You have any question about this? This is just okay, giving you an overview okay, about how we can model circuits in Verilog. I'm going to go into the details and show you some examples, but please interrupt me if you have any question about this. So what we have seen in the previous slide, I talked about data flow and behavioral. So there is a small difference between these two. In the case of data flow modeling, we use the continuous assign statement. It starts with the assign keyword. We have already seen that. And we can use Boolean equations to describe combinational logic. Okay, and this is actually what exists in the second assignment. Okay, when you would like to describe a BCD adder, you have to use Boolean equations, okay, to describe the output of the BCD adder. And Verilog provides a rich set of operators. Already we have studied some operators like the AND, the OR, the NOT, the XOR. Okay, so we can use all of these operators, but there are also other operators that you can also use, okay, when you are using the continuous assign statement, when you would like to write expressions. So these operators are very useful and very powerful. We can use them to describe adders, comparators, multiplexers, etc. And the synthesis tool, okay, can map this description into a target technology. And you can have a tool which is called synthesis tool because it can generate a circuit out of this description. So not only you can use a simulator to verify the correctness. Okay, this is what we are doing actually in these Verilog assignments. We are using a simulator, but you can also use another tool that can generate a real circuit, okay, out of this description, okay, from this description in Verilog. You can actually have a circuit, or you can map this circuit into, you can have it on an FPGA, which is a field programmable gate array, as you are doing, for example, in the lab. Some of you are doing this in the lab. So you can have your circuit on a chip and you can test it in the lab. So this is really very useful and very powerful. So you can model and you can have a prototype of your circuit. If you would like to have a real chip, you can take this Verilog description and you can give it to a chip manufacturer, and he can actually have your circuit implemented on a real chip, or you can have your entire system or your entire design implemented on a real chip. So all of this is possible. So this is called data flow modeling using continuous assignment. You can also have behavioral modeling. So behavioral modeling here, we can use procedural blocks and procedural statements. So what we are describing is that we are describing what the circuit does at algorithmic level. So you can write, let us say, if statements, case statements, all of these can appear as procedural statements. The same way that you describe software, you can describe hardware. So this is a higher level of abstraction that you can use in Verilog, and it encourages designers to build prototypes of their circuits. And you can actually have a quick prototype using this high-level behavioral description. And you can easily verify it with a simulator. So you can use the simulator to verify the correctness of your design. Now, some of these statements can be synthesized, are synthesizable. And for example, you might have an if statement in your code, and the synthesis tool might generate a, let us say, a multiplexer for that. So it can convert these statements into circuits. Now, sometimes some of these are synthesizable, other statements might not be synthesizable. So not all the statements which are provided in Verilog can be synthesized. Okay, some of them are. We have already seen the continuous assignment, so let me go over it one more time. So this is the syntax. You write assign is a keyword. The delay here is optional. Then you provide the name of a net. Here the net can be a wire or an output of a given module. And then you have the assignment operator, and then you have an expression. So this is the syntax of continuous assignment. So what we are doing is that we are assigning the expression to this net name. So when I say here by net, it could be a wire or it could be an output port. Okay. So this is what I mean here by in net name. The delay here is optional. You can use here hash delay, and it indicates that the assignment is delayed. So basically, you are delaying, okay, the output, okay, or you are delaying the assignment. You can have multiple of these assigned statements inside the same module, and these are concurrent. It means that you can have many of these, and you are describing, you have all of them, okay. Concurrent means that they can, if you are simulating them, you are simulating them in parallel at the same time. So they are happening at the same time. That's the meaning of concurrent. They are parallel, okay, because they are describing parallel hardware. So these continuous assignments are describing parallel hardware, and this is why they are parallel or concurrent. And they can appear in any order. So it does not really matter in what order these continuous assigned statements appear. You can use them to model combinational circuits, as we have been doing so far. We can describe the flow of data between the input and the output. So that's the reason why we have these continuous. They are very easy to use. So Verilog provides a very rich set of operators. Some of them we have already studied before. For example, we have the NOT operator, we have the AND operator, we have the OR operator, we have the XOR. We have already seen these operators before in a previous presentation. We have the NOT XOR. You can write it like this or like this. So this is exclusive NOR. Okay, so you can write the NOT before the XOR or after it. It means the same thing. We have reduction operators. I did not talk about these. We're going to see some examples. So you can apply the AND here. Okay, so if you have A as a bit vector, you can apply AND to all the bits of A. So notice that how we write the AND before the A. It means I would like to AND all the bits of A. So this is reduction AND. So I would like to reduce all the bits of A to just one bit. So we are ANDing all the bits of A to produce only one bit result. You can OR all the bits of A, that's reduction OR. You can XOR all the bits of A. You can say not AND, this will be NAND. We are NANDing all the bits of A. Not OR, that will be NOR. And we have not XOR, that will be the exclusive NOR. So all of these are reduction operators which are defined in Verilog. In addition, we have arithmetic operators. Okay, so we can write A plus B. Now that's addition. It does not really mean this is OR. Okay, so the plus in Verilog means addition, whereas the vertical bar, which is shown here, means ORing. So you have to distinguish between these two. So that would be interesting. I'm going to show you an example about that. So you can actually use the add operator. You can do addition in Verilog. You can do subtraction. You can do negation. You can do multiplication. You can do division. You can actually obtain the remainder. Like you do in any software programming language, you can also do it in Verilog. The difference is that if you write something like this in Verilog, if you write A plus B, then it indicates that then the Verilog will understand, okay, the synthesis tool is going to generate an adder in the hardware for you. So it's very simple in Verilog. You write A plus B, and there will be an adder circuit inside the hardware. That's what it means. You can use relational operators in Verilog, like A equal to B. So not written here equal. Equal, that indicates equality. You have not equal. You have less than, greater than, less than or equal, greater than or equal. So all of these are relational operators that exist in Verilog. We also have shift operators. So this indicates shift left, and this indicates shift right. So you can shift the bits to the left, you can shift the bits to the right. And we have two more miscellaneous operators which are very useful. Okay, the first one is called the conditional operator. So here we can have a selection select here is a Boolean expression that evaluates to true or false. If it is true, we select A. If it is false, we select B. This is called conditional operator. This is very useful. For example, we can use it to model a multiplexer. Okay, so the multiplexer is used for selection, and it can be modeled using the conditional operator in Verilog. We also have the concatenation operator. This is also very useful and very flexible. So you can concatenate the bits of A and B. So A can be a bit vector, B can be a bit vector, and you can actually concatenate the bits. So this is known. So these curly brackets, okay, these are known as the concatenate operator in Verilog. I'm going to show you some examples about that. Let me start with bit vectors in Verilog. I already talked about bit vectors in a previous lecture. I would like to go over them one more time. If you recall my lecture about combinational circuit design, I talked about bit vectors. So a bit vector is a multi-bit declaration. It uses the same name, but for multiple bits. You can specify the bit vector as a range, and you can specify here the most significant bit, the column, the least significant bit. This is the syntax. This is how you define a bit vector in Verilog. You can actually have a bit vector for input, for output, for wires. It does not really matter. So for example, here you can have A. A is a bit vector. It's 15 down to 0. So the most significant bit is 15. The least significant bit is 0. And A is an input. It's an input bit vector. B here is an output bit vector. You can see the output keyword. Now notice that here 0 is my most significant bit and 15 is the least significant bit. So notice that the bit ordering was reversed. Okay, so you have to be very careful. Both are allowed in Verilog, but you have to actually indicate that which bit is the most significant bit and which one is the least significant bit. You can also have wires as bit vectors. Yani for example, W here, notice that it's wire, and also it is a bit vector 3 down to 0. Now you can index a bit vector. This is called bit select. Yani you can select bit 1 of W, or you can have a part select. You can select not just one bit, but a group of bits. So for example, you can write something like this, A11 down to 8. So we are selecting 4 bits of A, bit 11, 10, 9, and 8. So this is basically a 4-bit select of A in this range. Now notice that the range here, the ordering of the bits, when you do a part select, it has to match, okay, the way they are declared in A. So A here, 15 is the most significant bit and 0 is the least significant bit. So this is why we start at 11 and we end at 8 when we select a part of A. Okay, so this is called a part select. So you have to have, it has to be consistent. You must be consistent with the vector declaration. So when you define the bit vector and you would like to select, okay, a part of this bit vector, you have to be consistent with the way it was declared initially. Any questions about this? Is this clear so far? Already we have seen this topic before. I'm just revising it with you. Let me show you some examples that we did not really do before about the reduction operators. So here I have a module which is called reduce. Okay, this is just actually for you to try some of these operators. So A and B here are inputs. You can see here A and B are inputs and they are bit vector 3 down to 0. X, Y, and Z, these are outputs. These are single bits. So we have 1 bit for X, 1 bit for Y, and 1 bit for Z. Now you can say here, for example, you can use the, you can do here OR reduction. So notice that I'm writing here OR A. Now A here is a bit vector. So basically it's the same thing as writing A OR and then writing here A 3 down to 0. So when you write A, it means 3 down to 0. This is basically the bit vector. So it means that I would like to OR these 4 bits and reduce them to 1 bit. So it will be A3 or A2 or A1 or A0. So we are just reducing it to 1 bit X And you can see that here X, as if we are using a 4-input OR gate, and the output is X. You can do here, for example, ANDing. Okay, for example, this will be AND reduction. That will be AND B. So we are reducing these 4 bits, okay, of B to just 1 bit. So if any one of them is a 0, you get 0. If all of them are 1s, you get the value of Y equal to 1. So this will be equivalent to a 4-bit, okay, to a 4-input, sorry, AND gate. So this will be like B0. This will be B1, B2, and B3. And the output here is Y. So this description in Verilog is going to produce a 4-input AND gate. You can also do here reduction XOR. So notice that this is XOR B. So we're XORing all the bits of B, and then we are ANDing it with X. Okay, so X here is just 1 bit, and this will give me Z. Okay. So this is the meaning. This is the meaning of reduction operators in Verilog. You are very silent today. You understand all of this? Is this clear? So we're going to practice using this. We're going to have actually more assignments in Verilog. Okay, maybe a 3rd assignment soon, inshallah. Okay, in which we use these operators. Now, another important operator is the concatenation operator. So that's the concatenation operator. That's very useful and very powerful in Verilog. So here A and B are bit vectors. These are inputs. 7 down to 0. So these are 8-bit vectors. And X, Y, Z are outputs, and these are also bit vectors, 7 down to 0. That's here for X, Y, Z. Now, suppose I would like to shift A 3 bits to the right. So when I shift A 3 bits to the right, then I'm going to insert 3 zeros. So what I can do is that I can concatenate. So this is the concatenation operator. So here 3B, it means that 3 bits in binary, 0, 0, 0. So the upper 3 bits of X will be 0, 0, 0. And the remaining 5 bits will be A7 down to 3. So this is X here, which means the same thing as X7 down to 0. So notice that from 7 down to 7, 6, and 5 will be 0, 0, 0. So these are the upper 3 bits of X. And the lower 5 bits of X will be A7 down to 3. So it's like we are shifting A, okay, 3 bits to the right, and we are assigning it to X. You can rotate the bits if you would like. Yes, question?
Yes, sorry, but I would ask about that 3 before the B. Is it optional or mandatory?
Well, in the case of concatenation, you have to specify the number of bits. If you don't specify the 3 inside the concatenation operator, the Verilog compiler will generate an error for you because it might not really be sure that how many bits you mean by that. So it's important to specify 3 bits, okay? Indicate 3 before the quotation and the B when you are dealing with the concatenation, because you would like to specify a certain number of bits. So to remove any ambiguity, it's important to specify the number of bits. Yeah, ma'am?
Okay, thank you.
All right. Right. I do have other examples. Like, for example, here, Y. Now, you can actually rotate the bits. Yani, for example, you can take the lower 3 bits of A and make them the upper 3 bits of Y. So here, Y means Y7 down to 0, because Y here is a bit vector. So from 7, 6, 5, 7 down to 5, it will be A2 to 0. So we're taking the least significant 3 bits of A and making them the upper 3 bits of Y. And we are taking the upper 5 bits of A and making them the lower 5 bits of Y. So notice that we have done this using actually selecting a part selecting some bits of A, and then we are doing concatenation. So this is the importance of the concatenation operator and using the part select, okay, selecting certain bits of A. You can even select bits of A and bits of B. I also have here a third example. So here Z, it means that's Z7 down to 0. So 7 and 6 will be A5, 4. So this will be the upper 2 bits of Z. Then this is B. So we're using a different here input B, 6 down to 3. This will be actually 4 bits of B. And then here we have the lower 2 bits of A. So notice that we can take some bits of A, some bits of B, we can concatenate them, and we can assign them to the output C. Okay? So this is very useful, very powerful. It allows a lot of flexibility when you would like to describe something like this in Verilog. Okay? So this is the meaning of the concatenation operator. We have seen the integer literals. These are the constant values that can appear, okay, when you are describing circuits in Verilog. So the syntax is like this. You provide size. Now, sometimes size is optional, but if you are using it inside the concatenation operator, you have to specify it. Then you have the quotation here, the quote and the base, and then you have the value. So the size here indicates that the number of bits. So how many bits you have in this value? Yeah, for example, here I specified the size to be 3 bits. So 3. And then this is followed here by quotation base. You can use quotation B, single quote. Notice the syntax. So B means binary, O means octal, D means decimal, and H means hexadecimal. And then you have finally you have the value. So the value here can appear in binary. If you are using the base to be B, binary, you have to show the value in binary. If it is octal, you have to show it in octal, in decimal or hexadecimal, depending, of course, on the base. And if you don't specify the base, then the assumption it will be decimal. And if you write an integer without specifying the base, by default, the base will be decimal. I have some examples. For example, when I say here 8, it means that 8 bits, the base is binary, and you can write here 8 bits in binary. Notice that you can write an underscore. This is for clarity, to enhance the readability. Okay, the underscore is ignored, of course, by Verilog, but you can actually write it to enhance the readability when you have a large number of bits and you would like to group them. You can, for example, take a group of 4 bits and you can put underscore in between. So this will be an 8-bit binary value. This will be, for example, a 16-bit hexadecimal. Notice that I did not rewrite the size. Okay, the compiler can sometimes infer the size, okay, from the number. You can write here, for example, 16, indicating 16 bits, and show the value in octal. Notice here the quote O. You can say 32, indicating 32 bits, okay, and D indicating decimal, and then 999. Now, 999 does not require 32 bits, so the upper bits in binary will be all zeros. So we are representing 999 in binary, so it's going to be converted to binary, okay, and it will consist of 32 bits. That's the indication here of 32. Now, let me show you more examples before we leave today. I'm going to show you already we have seen this example before, so I'm not going to spend time on this. Remember the combinational circuit design, I talked about the ripple carry adder. Already we have seen this before. So basically we're using identical copies of a full adder to build a large adder. So the cell here is my full adder, and basically you are connecting these full adders. So we can describe this using array instantiation. So we can describe the structure of this 16-bit adder. So I can use here adder 16. Notice that the inputs here, A and B, are 16-bit vectors. The sum is a 16-bit vector. There is only 1 bit which is carry in and 1 bit which is the carry out. So this is my output carry. And you can describe this using array instantiation. Already we have done this. Just go back to a previous lecture when I talked about combinational circuits. So full adder here is the name of my module, which is full adder. That will be just one full adder. And then this is the name of the instance, and you have an array of these. So notice that 15 down to 0, this is going to create 16 copies of the full adder. Okay, and notice the inputs here, and notice the outputs. So this is called array instantiation, as if you have 16 instances of full adder. You can describe the same 16-bit adder using continuous assignment. We also have done this before, if you recall. So the same inputs, the same outputs, okay? However, I'm using here continuous assignment to describe the sum and the carries. And notice that I'm using here Boolean expressions on bit vectors. So this is the expression here for sum. This is the expression here for the carries, okay? So continuous assignment, okay? That's a second description for the 16-bit adder. So we have seen model instantiation. This is one description. Continuous assignment is easier. Why? Because you don't really have to instantiate. You can describe the same thing using continuous assignment and Boolean expressions. This is a third description. Now that's even is more interesting. That's actually here the same inputs, the same outputs. Notice that A and B are 16-bit vectors. The sum is also a 16-bit vector. It's the same inputs, the same output. This is also a 16-bit adder. But look at this description. It is just one line. Verilog allows you to describe an adder this way. So we are saying in one continuous assignment that C out and sum is A plus B plus C in. We are using the plus operator. That's addition. So we're adding A, which is 16-bit vector. So this is 16 bits here. Okay. This is plus 16 bits plus 1 bit. Okay. This will produce 17 bits. The sum will be 16 bits. So notice that sum here as the lower 16 bits, and C out is 1 bit. So notice that we are using the concatenation operator to produce the C out and sum. And we are doing it in just one continuous assignment. And we are using the plus operator. So here the synthesis tool, the Verilog understands this, that you need actually an adder inside your circuit. It's going to generate an adder from this description. You see how simple it is? That also is a third description of a 16-bit adder using the plus operator. Let me show you how we can parameterize this adder. We can use a parameter. Now, here what we have seen in the previous slide is a 16-bit adder. Like, what if you would like a 32-bit adder or a smaller 8-bit adder? You have to have another module for the 32-bit adder and the third module for the 8-bit adder and so on. Yani you need actually to change the description every time you change the size of this adder? Well, Verilog has a nice way of doing it. You can use parameters to define a generic adder, okay, of any size. And the way to do it is to describe it like this. So you can define here a module which is called adder. And this adder has a parameter n. So that's my parameter n. Notice the syntax. You use hash. And between parentheses, you specify the parameter n. And you can define here a default value, which is 16. That indicates the default value of n. Now, you may or may not specify the default value. The default value is optional. But I'm showing a default value here, which is 16. Now, notice that A and B now are inputs, but they are defined in terms of n. So notice that they are n minus 1 down to 0. So notice I'm using n here. So if n equal to 16, it will be 15 down to 0. If n is equal to 32, then it will be 31 down to 0, etc. Okay, so these are my inputs A and B. And my output sum is also described in terms of n. So it's also a bit vector, n minus 1 down to 0. So it consists of n bits. The C in is just 1 bit and the C out is just 1 bit. Again, we are describing this using continuous assignment, the same statement. So regardless of how many bits you have in A and how many bits you have in B, you can add A plus B plus C in. So you are adding n bits plus 1 bit. This will give you n plus 1 bits. So you have here n bits for sum and you have here only 1 bit for cout. So this is n bits, this is n bits, and this is just 1 bit. Okay. So you can describe it generically like this, and therefore this is going to produce an n-bit adder. Now, the problem with this is that what is the value of this n? Well, we are showing here a default value, which is 16. But how about if I would like to use a different value than 16? So how can you change this parameter n? Well, the answer is that the way to change the value of n is that when you instantiate this adder. So here you are describing a module which is called adder, and this module is using a parametric. It's going to use it's using a parameter n. So this is actually a parametric description for an n-bit adder. But we are not really using the adder yet. In order to use this adder, you can instantiate it. For example, if you would like to test it in a test bench, you have to create an instance of this adder. At that time, you have to specify the value of the parameter n. So when you instantiate the adder, you specify the value of n. If you would like to use this adder inside another adder, when you instantiate it, you specify the value of n. So let us now instantiate adders of various sizes. Suppose I would like to have a 16-bit adder. You write adder here, which is the name of the module, and then hash 16. Now that will be the value of n. So n becomes 16. You can give it a name, which is adder 16. Now notice that A1 and B1, these must be 16-bit input vectors. Cn is just one input. Sum1 will be a 16-bit output vector, and Cout is just a 1-bit output. So you must specify A1, B1, and Sum1 to be 16-bit vectors. If you would like to have a different size of an adder, you can use, for example, hash 32. So it means that the value of n here becomes 32. So when you are instantiating the adder, you are changing the value of n. So the value of n here changes, okay, when you instantiate the adder. So here I would like to have a 32-bit adder. So A2, B2, and Sum2 must be 32-bit vectors, okay? So they are no longer 16-bit, they are now 32-bit vectors. Now, if you don't specify the parameter n, like here, then by default, it will assume the value of 16 because we provided here a default value for n, which is 16. So if you omit the value, if you omit hash and between parentheses the value of n, then it will default to 16 because we have specified the default value for n. As I said, the default value is optional. Yani you don't even have to specify this is equal to 16. If you don't specify a default value for n, then you must specify the value of n when you instantiate this module. I will give you another example about that. So if you don't specify the default value and you write something like this, then the compiler will not really accept it because you have to provide, okay, the value of n. But since we have a default value, then if there is no value here for n which is specified, then the compiler will take its default value. That's the meaning of the default value for the parameter. Right. So that's how we instantiate adders of various sizes. Is this clear? Do you have any question about this? You understand this perfectly? I do have other examples. In fact, I have many examples about this. Let us take a look how we can model a magnitude comparator. Okay, so in the case of a magnitude comparator, I have two inputs, A and B. Now, these can be n-bit vectors. You can see these are bit vectors, and each one consists of n bits. So I can describe here my comparator to have here hash parameter n. Notice that here I did not really use a default value for the parameter. It's enough to specify the parameter is n without specifying any default value. That's okay. And then the inputs A and B, notice that A and B use the parameter n. So it's actually bit vectors, n minus 1 down to 0. And there are three outputs: greater than, equal, and less than. These are the outputs of the magnitude comparator. Now, we can describe this magnitude comparator as we did before as an iterative circuit, and we can describe the equations, okay, for equal, for greater than, for less than. We can do that, okay? We can describe this as an iterative circuit, and we can do this, we can describe this cell, we can design this cell, and we can repeat this cell n times according to n, how many bits we have in the inputs. But we are not going to do it like this. We're going to use the greater than operator. We are going to use the equal operator, and we are going to use the less than operator. So we can compare using these operators, okay, in Verilog. And this is very easy and very simple. So when you use the greater than, equal, and less than, okay, if you are using a synthesis tool, it means that you would like to have here a magnitude comparator. So the output here can be either true or false, okay, 1 or 0. So this is why we get here the output is just 1 bit, okay, greater than, equal, and less than. But the inputs can consist of n bits. So you can compare n bits with n bits, and the output is just a single bit. So this is an example about how we can describe an n-bit magnitude comparator in Verilog, and we have described it at a high level because we use these operators, these three operators here, for comparison, okay, for testing if A is a greater than, equal, or less than. And if we are going to synthesize this, then the logic synthesizer is going to generate. So basically, I need a tool that can look at this Verilog description and generate a circuit for me. So rather than me describing all the equations of this magnitude comparator, the tool can do it automatically for us. So that's the beauty of Verilog, is that you can describe the circuit at a high level, and you can use a tool that will actually generate the circuit for you. Okay. Now, this magnitude comparator has a parameter n, but there is no default value for n. So now we cannot actually use it as is. So what you have to do is that you have to instantiate this comparator. If you would like to test it, and you would like to simulate it, you can use a test bench, and you can instantiate it inside the test bench. So when you instantiate, you have to provide the value of n. If you would like to use this comparator inside another module, for example, you would like to design another module and you would like to use a comparator inside it, you can instantiate it, okay, inside another design module, okay, and you can specify the value of n. So this is how we instantiate comparators of various sizes. If I would like to have a 16-bit comparator, use the name of the module, which is comparator #16. This will indicate the value of n. So now A1 and B1 must be 16-bit vectors because you specified here n to be equal to 16. That's the meaning here of #16. So you must provide the value of the parameter n. Here, for example, you would like to have a 32-bit adder. You are using here 32-bit comparator, not adder, 32-bit comparator. Then you must use here #32. So now n will be equal to 32. So now A2 and B2 will be 32-bit vectors. Okay, you have to declare them as 32-bit vectors. Now, if you instantiate a comparator without specifying n, then you get here the error message from the compiler. It will tell you what is the value of n. Now, there is no default value. We did not specify any default value for n. So therefore, the compiler will not really know what's the value of n. So here, this will be a wrong instantiation. You must specify the value of n if there is no default value. If there is a default value, then it will assume its default value if there is no value for n when you instantiate the comparator. Okay? So you have to be careful about this. Okay, how you instantiate modules that have parameters. You have to specify the value of the parameter when you instantiate the module. طيب, any question about this? Is everything is clear? طيب, good. As I said, Okay, I have more and more examples. So all of this presentation will be full of examples. Let me show you one more operator, which is called the conditional operator. We have seen many operators. And for example, here we have seen, okay, the greater than operator, the equal operator, less than operator. These actually are very powerful. You can actually use them to compare or to generate comparators. The plus operator, we use it actually to produce an adder. Okay, what else? We have this conditional operator. The syntax is similar to the syntax which is used in high-level programming languages. Okay, so you write it like this. You write a Boolean expression, and then a question mark, and then you write a true expression, followed by a colon, followed by a false expression. This is the syntax. It means that if the Boolean expression is true, we select the true expression. And if the Boolean expression is false, we select the false expression. Now, this is useful actually for describing multiplexers because we are selecting. So that will be actually a perfect operator actually for selection. And when you use it, then the compiler will know that what you mean by this is a multiplexer because you are selecting. So that's basically the multiplexer because the multiplexer is used for selection. So the syntax is very similar to syntax which is used, for example, in the C programming language. The C programming language was invented back in the 1970s, so 50 years ago. And it uses this syntax actually in software. So we use conditional operators in software when you are actually executing, let us say, these conditional expressions. But we are also using it to describe hardware. Now, that's actually is interesting, is that we are using the same operator for describing hardware in Verilog. So it has exactly the same syntax, which is used in a high-level programming language. Let us take a look at these examples. Suppose I would like to design a circuit that can output the maximum of two numbers A and B. So here A and B can be bit vectors. So I can check if A is greater than B. If this is true, we select A. If this is false, we select B. And this will give me max. So I'm describing this with continuous assignment. So this continuous assignment is describing a circuit. And this circuit has a comparator that can check if A is greater than B. And it has a multiplexer that can select the output. So the maximum will be the output of this circuit. It's going to select either A or B. So this is why we need a multiplexer. So we use the output of the comparator to select. So we use the select input of the multiplexer, and the inputs of the multiplexers are A and B, and the output is max. Okay. If you would like to assign the minimum, you just need to reverse the order of A and B. So this becomes B, and this becomes A, and therefore we are selecting the minimum. So that's interesting, is that how we can use the conditional operator, okay, for describing a multiplexer. Let me show you how we can model a 2x1 multiplexer purely in Verilog. That will be very easy and very simple. So here I have a module which is called mux2. The 2 here indicates that we have two data inputs, A and B. So A and B here are n bit vectors, n minus 1 down to 0. So I'm using a parameter n. There is a default value which is equal to 1, but this is not really necessary. Okay, it's optional to have a default value. So A and B are n bit vectors. And there is here an input which is select. That's my select input. These are A and B. And the output is Z. Notice that Z here is my output. It's also an n bit vector. Okay. So if I would like to describe this multiplexer, I'm going to use continuous assignment. This is here my assign keyword. The output is Z. Here the inputs are select A and B. So here we have to check if select equal to 0. So if this select equal to 0, we select A. So here Z becomes A, else Z becomes B. So that's an if-else statement, okay, which is described by this conditional operator. Okay, you see how simple it is? So now we have another very useful operator, which is the conditional operator for describing a multiplexer. And this multiplexer is parametric, we have a parameter which is n. So when you would like to instantiate this multiplexer, okay, you can actually instantiate with n equal to 1, n equal to 2, n equal to 8, 16, whatever. Okay, you can actually specify whatever is the number of bits in A and B and the output Z. You are very silent today. Any questions about this? Okay, let me ask you this question. How was the last assignment, second Verilog assignment? Was it easy? Was it difficult? Since you are very silent today. So I noticed that some of you have raised many questions. Yes, تفضل وليد, تفضل.
After today lecture or before today lecture? Because
well, we talked about this topic before. I was talking about actually model instantiation. Yeah, I'm talking about parameters and parametric.
Quite easy now. It's quite easy now.
Now it becomes actually easier, right?
Yeah.
We're going to have, inshallah, come in another third Verilog assignment soon, inshallah. طيب. Let me talk about a 4x1 multiplexer. Okay, so here in this 4x1 multiplexer, I have 4 inputs A, B, C, D. These are bit vectors. You can see here A, B, C, D, n minus 1 down to 0. And here is the parameter. Okay, notice the syntax. We write here hash. Between parentheses, we write parameter equal to 1. This is the default value. And if you don't specify n, it will default to 1. It means that A, B, C, D are just single bit inputs. Now we have 2 bits for selection. You can still see here that select here consists of 2 bits, 1 down to 0. And we have the output Z is also an n-bit vector. So we can also describe this with conditional operators, but these are nested. So I can use select. So you notice that how we are nesting the conditional operators. So if select 1 equal to 0, I'm going to select this expression. Otherwise, if select is equal to select 1, notice that select 1 is 1 bit of select, the most significant bit. So this select here consists of 2 bits, 1 and 0. Okay, 2 bits. So notice that here I'm using 2 wires. I'm showing 2 wires for selection. Else, if select 1 is equal to 1, we're going to select this expression here. Now that's actually for select 1. Inside, we can look at select 0. So if it is 0, we select A. If it is 1, we select B. So now here we have 0, 0, we get A. 0, 1, we get B. If this is equal to 1, then we go here. So we get 1, 0, we get C, and 1, 1, we get D. So this will give me actually all the 4 possible combinations, okay, for my 2 input select. So selection here consists of 2 bits. It does not depend on n. Notice that select does not depend on n. It is just 2 bits, regardless of n. Okay. So here we have like nested conditional operators. So basically, we are using conditional operator inside another conditional operators, and we are using this to model a 4x1 multiplexer. Now you can think about this as 3 2x1 multiplexer. Yani this will be 2x1 mux. So this will be mux 2. You can think about it. This is a mux 2. This is another mux 2, and the entire thing here is also a mux 2. So you can think about this 4x1 multiplexer as implemented using 3 small 2x1 multiplexers. Okay, so we are modeling it, okay, this way using nested conditional operators. So that's really good. Okay, so that's basically how we can model things in Verilog.